This is the first in a series of videos that I'm going to do talking about differential equations, and this is going to be at a very introductory level. So let me start off by saying something about what I'm not going to cover. So solution methods are something that you would usually cover in a differential equations course. And that is how do you take a differential equation and manipulate it in some way to end up finding a solution to that equation. So I am not going to talk about that. I'm going to take a first brush at this, something that would be accessible within a calculus course, for example. So we're not going to talk about solution methods. Instead, some of the ideas that I'm going to touch on in this series. So we'll focus on verifying that a given solution or a given function is a solution to a differential equation. So there I would say, here is a function. I think it's a solution. You tell me whether it is or isn't. And then another method, this is actually kind of a method for solving, a differential equation, but it's kind of like verifying, and it's called an ansatz method. So using ansatzes, and these are really educated guesses. And the idea here is, that you're not given a solution and you're to check, but you're given, or you have some rough idea of what the solution might look like, and you use that knowledge to come up with a pretty good guess, and maybe there's a parameter, an unknown quantity in your guess, and you plug it in and figure out what that quantity is. So it's similar to verifying that a function is a solution, but it's not knowing the full detail of it and using that to simplify your problem. So let me first start off here with a different type of equation, an algebraic equation, which is familiar, I'm sure, to anybody who's watching this video, I hope. So an algebraic equation is something like x cubed minus 2x squared plus x equals 0. And we call this an algebraic equation because it's basically an unknown quantity, an unknown number, x, and we have done something to it, multiplied it by itself a few times, and added and subtracted things of this type, and imposed a constraint on it. So multiply the number by itself 3 times, subtract 2 times the number multiplied by itself twice, and then add the number again, and that should come out to 0. So is there an x that makes this work? So here the answers are going to be numbers. So in other words, when we find an x, that x value is going to be a number. Maybe we'll find a few different values of x, but each one solves this on its own separately as an individual number. So instead of coming up with a method for solving this, I'm going to do what I'm going to focus on in this video, which is, at least to start with, I'm going to show verifying that a given function is a solution. So here I'm going to ask, well, let's verify that x equal 1 is a solution to this. What does it mean to do that? And this is something that you should do anytime you solve an algebraic equation, you get an answer. You should go back and plug it in and check to see that you got it right. So that would be a final step of solving an algebraic equation. Okay, so I'm going to switch to green for calculations, just to add a little bit of color variety so it doesn't get too monotonous blue here. So we think that 1 is a solution, so we take 1 and we plug it into the equation everywhere that an x appears. And so we get 1 cubed minus 2 times 1 squared plus 1, and that is equal to 1 minus 2 plus 1, and if I add those up, we see that that comes out to 0. Now it just came out to 0, we didn't impose that, and what that tells us is that it actually, 1 does solve this equation, because if we just plug it in, the number that we get is equal to 0, and that's what we were looking for up here in this equation. Okay, so there's other solutions to this, but I'll leave that for you to use if you want to practice your algebraic equation solving. Here we're going to focus on differential equations. So the big difference between a differential equation and an algebraic equation. So a differential equation is one that involves a function and its derivative. So what do I mean by that? Let's say we have the derivative of y with respect to x is equal to, let's say y squared minus 1. There's a differential equation. There's a function. I haven't written it out with an of x, but we can just put a reminder here on the side. Y is a function of x, and if I take its derivative should be equal to itself squared minus 1 at every value of x. Okay, so here the unknown now is a function, and that's different from what it was in an algebraic equation. In the algebraic equation, the unknown was just a number. Okay, so let's see an example here. I'm not going to solve this equation here or to even propose a solution to it. What I'm going to do is give you a new one that's maybe familiar from earlier work in the course. So let's check whether y equal 4e to the 3x solves y prime equal 3 times y. Okay, so first thing we have to do is, as in this example here, the algebraic equation, where we took the number and we cubed it and then we squared it. So we cubed it, we squared it, we multiplied it by 2, took the difference, added 1, and so on. Here we're going to have to do similar types of things, but in this case the equation says take its derivative and multiply it by 3. So I'm going to take its derivative, y prime, and now I'm thinking about this function up here. So I take the derivative of 4 times e to the 3x, there's a chain rule, and I end up with 4e to the 3x. Derivative of an exponential function is itself, but now by the chain rule I have to multiply by a 3, and there I get 12 times e to the 3x. So that is the derivative, and that's the quantity that I want to put on this side. And now let's compare that to the quantity on the other side, which is 3 times y. So there I take 3 and I multiply it by 4e to the 3x. And when I calculate that, I get 12 times e to the 3x. So I've calculated what's on the left-hand side, I've calculated what's on the right-hand side, and you can see here that they're equal. So I have verified that this function, 4e to the 3x, satisfies this differential equation. So that means that we can say that y of x is a solution to the equation y prime equal 3y. Just like x equal 1 was a solution to the equation x cubed minus 2x squared plus x equals 0. Okay, so you'll notice in this whole process here that the 4 just got carried along for the ride. It got multiplied by 3 in both cases, and it actually could have been anything. And so what we can hypothesize then is that c, any constant multiplied by e to the 3x, is also going to be a solution to this differential equation. And we can plug that in and check. If you take y prime, we get, again, there's going to be a chain rule in there, and we get e to the 3x, ce to the 3x multiplied by 3. And then if we just multiply y by 3, we get 3 times ce to the 3x. And you can see it doesn't matter if we put the 3 in the front or in the back. These two are going to be equal, so we have found a general solution, which a general solution is something that solves a function that solves the differential equation and has an arbitrary constant in it. And we can pick that constant according to some extra rule that we call an initial condition. So instead of getting this arbitrary constant, we might say to get a single solution, we can impose an initial condition. Sometimes I'll refer to that as an IC, initial condition. And you can think of that as being the beginning state of an experiment. So what often happens is your differential equation describes some law of physics or some law in biology, for example, a growth law for a population or a circuit law for a current in an electrical circuit. And the initial condition describes how that physical law is going to be started off in some particular experiment. So for example, with population growth, well, let's say we have some differential equation that describes the growth of a population. The initial condition would be, what is the population size at the very beginning of that experiment or that observation period? Okay, so for example, then we could have a problem like this. Find the solution to y prime equal 3y that satisfies the initial condition y of 5 equal 2. Now when we say initial, it's often going to be the case that we choose the initial point to be at 0, so x or t equals 0, but that's not necessary. So here I'm intentionally picking an initial time or an initial point x that's at 5. And so this is, you can think of this as just being that not all experiments start at time 0. We might use the clock time, in which case if our experiment starts at 5 in the afternoon, then we would have a y of 5 case or condition. So in this example, we've already seen that we have a solution to this up here, which was y of x is c times e to the 3x. And now, with our initial condition, we can plug in 5, and we know that we want to get out 2, but what does it look like in the function? It looks like c e to the 3 times 5, which is c e to the 15, and we want that to be equal to 2. So we have to choose c equal 2 times e to the minus 15. And now we can write down y of x for this particular case, this particular initial condition with the differential equation. We have a solution that is 2e to the minus 15 e to the 3x. Now maybe this is a convenient way of writing down the solution. But what I'm going to do is just show you how to think about this in a slightly different way that makes it a little bit easier to understand how this solves the initial condition very quickly just looking at it. So I'm going to flip to the next page here and rewrite y of x is equal to 2e to the minus 15e to the 3x. And if I recombine these or combine these and factor out a 3, what I get is e to the 3x minus 15, and that is equal to 2e to the 3x minus 5. And now you could really easily see that when you plug in 5 in the brackets, you get a 0 in the power, and then all you're left with is 1, e to the 0 is 1, and a 2. So when you plug in 5 here, you get a 2 as the answer. So we see very easily in this form that the initial condition is satisfied. Okay, so that's a simple example of how to verify that a function is a solution. Now the examples get more complicated. I mean, you can have a much more complicated differential equation, but basically if it's a differential equation, as long as you know how to take derivatives, doesn't matter how complicated the expressions get, the principle is the same. You take the function that you're given, you plug it into the differential equation and see if you get the equation being satisfied by that function. Okay, so let's move on to a slightly more powerful method, and that is, I refer to it as more powerful because you don't need somebody else to give you the full function, and you're just sort of checking it with an ansatz method. If you have some reasonable idea of how a solution might look, you can use that to build a guess and then plug in and clean up the unknowns in your guess. So an ansatz is an educated guess at a solution that reduces the problem usually reduces the problem from a differential equation, dE, to an algebraic equation. Now, it doesn't always reduce it from a differential equation to an algebraic equation. The examples I'm going to talk about, that's the case. In general, it'll reduce a more complicated differential equation to a simpler one. Sometimes you could reduce, for example, a partial differential equation to an ordinary differential equation with an ansatz. I'm not going to talk about the difference between partial and ordinary differential equations, but just to give you the idea that this method is not quite as restricted as I'm going to describe here. But in all contexts, it's actually quite useful as long as you have some basic idea of how these functions or these differential equations solutions might look. Okay, so here I have a differential equation that involves the sum of three pieces. And it may seem a little bit surprising at first when I pull out a functional form that I think is going to satisfy this, but let me give you a little bit of a preview of why this functional form is useful. Imagine if we had a function that when you took its derivative and its second derivative, the basic function itself doesn't really change. In other words, taking a derivative doesn't really change the function itself, it just gives you extra numbers in front of it. And we've seen something like that. Y of t is equal to, I'm going to call it ae to the rt. And this a in front of it is actually not necessary, but I'm putting it in there so you can see what role it will play in the general method. And now just thinking ahead and with what I just said a few seconds ago, what happens when we take this ansatz, this educated guess, and plug it in? Well, what we're going to see is that the function itself has an e to the rt in it. When I take a derivative, this r is going to come out in front, but this part of it is going to stay the same. So I'll have e to the rt, e to the rt, and again e to the rt with a bunch of stuff out in front. And I can cancel those e to the rt's because the exact same form appears in all of the equations. Oops. So let's do that. Let's figure out what these are. So here I get a single derivative brings one r down, and a second derivative brings another r down. And now when I take these, and here I'll just draw a line so I have a little bit of room at the bottom, I plug this into the differential equation. So the y double prime comes up in front here, so I get an r squared a e to the rt. And then plus 3 times, and now I plug in the y prime, so that's r a e to the rt. And then plus 2 ae to the rt. And I want that to be equal to 0. So I'll set that equal to 0. And you can see now that the a will cancel from all terms because it's a common factor, and the e to the rt will cancel from all three terms. So now I get, so for the first principle there is that because the y prime, the y double prime, y prime, and y terms all appear without being squared or in any kind of complicated way, they appear in what we call a linear format. The a just factors out, and any multiple of the solution I find will also be a solution. And so now I have an equation that just involves the r. So r squared plus 3r plus 2 equals 0. And I can solve this by any method that we know for solving algebraic equations. So I'm just going to factor this into r plus 2, r plus 1. And we get that r equal minus 2 is a solution and r equal minus 1 is a solution. So that's the solution to this algebraic equation, but that also tells us that with those values of r, a e to the rt will also be a solution to this differential equation. So we now have that y of t equal any constant a, e to the minus 2t is a solution. And y of t equal any a equal e times e to the minus t is also a solution. Both of those two. So this is what I meant by taking an educated guess. Why should we assume that the solution has the form of an exponential? Just because we have this intuition that when we take derivatives, the form of the function doesn't change. All three forms will be the same, so the function part is going to drop out, and we're just left with an algebraic equation. So that's how we have an educated, this should be an educated guess at a solution. The educated guess reduces the problem to an algebraic equation. Okay, so let's try another one. Another example, slightly different. Here we're going to do x squared y double prime plus xy prime minus y equals 0. Sorry, just before I go on with this one, referring back here to this example. So in this case, it factored really nicely, right? We got these two real solutions to the equation. But if we had found no real solutions, for example, if we had found complex solutions, then we'd have to understand what an e to the complex number means. And that's a solvable problem, like we can figure that out, but it sort of shows you that the ansatz doesn't always work as we first expect it to. It doesn't give us an exponential function of the type we were hoping for. And the same thing is going to show up here, although again we're going to be able to solve it because I've chosen a special condition or a special equation that works pretty well. In other words, it's going to have real roots, just like the first example did. Okay, so now the thing to notice is that here, if I plug in e to the RT here, we'll have e to the RT in all three of these, but it's going to be multiplied by x squared here, x here, and a constant here, 1 or minus 1. And so those make the function a different form in each term, and it's not just going to cancel out. Those x's will never disappear. So an ansatz of e to the RT is not the best to use here. So instead, we're going to use something that matches better to the conditions that we have. And in particular, you'll notice that we have a zeroth derivative, a first derivative, and a second derivative. And as we go up in derivatives, we get more and more powers. And if you think about what happens to a power function, if y was a power function, this would be the highest power. Take one derivative, the power comes down by 1, but then I multiply by an x. And then take another derivative, the power comes down yet again, but I'm multiplying by an x squared. So if I choose an ansatz that is y of x equal x to the r, and I could choose an a in front here, but if you'll trust me, you'll see that the a is going to cancel just as it did here, so I'll leave it out for now, and I'll leave that as an exercise for you to include and see that any a multiplied by x to the r will work as long as we find r values that give us a solution. Okay, so now y prime is equal to rx to the r minus 1, because here r is just an unknown constant that we'd like to find. And then we have r minus 1, x r minus 2. And now we plug all of these in to the equation in proper way. So we get an x squared r minus 1 x to the r minus 2. That's a times there. Plus x times rx r to the minus 1 minus x to the r equals 0. And this is what I was getting at. Here you have an x multiplied by x to the r minus 1. Here you have an x squared times x to the r minus 2. And so in each case, we end up with an x to the r as the power function, because the extra x's fill in the gap that you lost from the derivatives. And now, just as in the previous example, the functional form is the same in all three terms, and we can cancel it out, and we're left with r minus 1 plus r minus 1 equals 0. And that is r squared from these two minus r from these two plus r minus 1. and that gives us r squared minus 1 equals 0. So now we can see that we have two roots, r equal minus 1 or r equal 1. And this is where, as I said before, we end up here in this case with a quadratic, but if I had had different coefficients in front, instead of 1, 1, and minus 1, it's possible to come up with an equation where what we end up here is complex roots, in which case this would be x to a complex number. And maybe if you're happy with power functions with complex powers, you understand what that function looks like, but I'm going to consider that to be outside the scope of what I would expect you to know. So what that means is that this educated guess will work for some differential equations, but it'll run you into trouble in others. Okay, so what is the equation, the solution, not just to the algebraic equation that we reduced to, but the original differential equation up here? We have y of x is equal to x to the minus 1, which is 1 over x. And we also have, I'll call that 1, and we also have y2 of x, second function, and I guess I could put subscripts here and here on the previous example, just to remind you that these are two different functions. And y2 of x is equal to x. Okay, so we really should check that these solve the differential equation. So without flipping the page, I'll just save a little space off here in the corner. Okay, so let's say for y1, if I take one derivative of y1, I get minus 1 over x squared. And if I take two derivatives of y1, I get 2 times 1 over x cubed. And now if I plug those into the differential equation, I get x squared times 2 times 1 over x cubed plus x times y prime, which is minus 1 over x squared. And then I get minus 1 over x. And the first expression here is 2 over x, once I cancel an x squared on top and bottom. In the next term, there's a minus and an x on top with an x squared on bottom. I get minus 1 over x, and then the last term is just as it is, 1 over x with a minus sign in front. And here you can see I have 2 minus 1 minus 1, that comes out to 0. And so we see that 1 over x does in fact satisfy the differential equation. Plugging in the other one is not too difficult to do. That's an easy, you can almost see it just inspecting it. So I'll leave that one out. Okay, so what I've covered here is two different sort of tasks that you'll need to sort of master, which is how to verify that a given solution, where is it here? Given solution is in fact a solution to a differential equation, and that requires just plugging it in, so calculating the y prime and the 3y. And then another example down here where we talk about initial conditions for these differential equations, and ansatzes, where we don't quite get a full solution, but we have a guess at what the solution looks like with an unknown constant in there, and we plug it in and use the differential equation to get a constraint on the constant, and then use that to find the actual solution or solutions to the differential equation. And so here we did two of those, one e to the rt type ansatz and another x to the r type ansatz. Okay, so I'll continue with another couple of videos on other methods in differential equations.